Milton, we've put ourselves into a position where we're looking at all the points on L2. We want to know what they look like when we map them into the surface now.
Okay, so plug back.
Yep. Take that and plug it into the original surface, 3y. Okay, we want to go back, rewrite the original surface, 3 for x, y stays y. So what does that become? 9 minus 6y plus 2y. So 9 minus 4y. Travis. We can. But Travis, what is that? When it's mapped up in there, what geometric shape do we have up there? Like, what does that look like? A line, right? And if it's a line, the only points that matter are the endpoints. So yes, you could take the derivative of this. It would be -4. You set it to 0, would have no solution. Then you go to the endpoints. So if you ever get a line here, you can actually just skip this step and go straight to the endpoints. All right? Now I'm going to put here, call this f of y. All right? Because this is really like a function of one variable. Yes?
What did you say about it being a line?
This is a linear expression, right? So as we start to move our points along here, the y value is changing, right? And in the surface, so like let's say we're moving along line 2 like this, right? Then up in the surface, we know that this is what it's doing. So up above us, it's acting like a line. So if you have a straight line, you can't have any maxes or mins in the middle. It's only at the endpoints that you have the max and mins. So we don't need to look in the middle. Okay? All right, so what? I've lost my spot. We're just going to look at the endpoints, right? So I'm going to do f of 0 and f of 2. And that's going into what? This right here, right? So what do we get? At 0 we get 9, and at 2 we get 1. And let's see, Quentin?
Yes.
I would like to know what these correspond to on our original surface. Like I want to be able to write this down. So it's like f of something something, f of something something. So what are those?
F of 3, 0.
3, 0?
And 3, 2.
3, 2. Good. See, we're on L2. X is always 3. Y is, well, the 2 points we found, so we plug those in. And we already have 3, 0, don't we? We don't have 3, 2 yet. So let's do that. What's f of 3, 2? I don't know. What is it? 9. 3 times 2, 6, 12. So 9 minus 12, -3. Is it 1? Has anyone done it yet? Yeah, 1? I'm getting 1. Do I have to write it out? I don't like arithmetic. I don't want to say hate it. You got 1? Okay, let's go with 1.
Don't we have it from
Oh yeah, we did. It's over. Yeah, we had it here. I forgot. Sorry. I thought we didn't. I'm not thinking. I'm just going to shut up. Y'all are doing better than me at this now, at this point. Okay. And it is Rose's turn. What now, Rose? L3. Tell me about the points on L3. Y is 2. And what about x? X is free, and x has to be between 0 to 3. Okay, so look, I mean, we've kind of like, we're scratching the record here over and over, right? Like this is the same process. Okay, so now we plug this in. And when we plug that in up there, x's stay x's, y's become 2's, and y's become 2's. Just agree. If you agree, let me know. Yes, no?
Yeah.
Okay. Fernando? Okay, there you are. What now? We've reduced this to a function of a single variable now. Take the derivative. Okay. So now we take our derivative, and this one is 2x minus 4. Now, Fernando, I took the derivative on this one. The previous problem I didn't. I didn't put prime, sorry. I didn't on the previous one because we said it was a line, right? This one is a parabola. So because it's a parabola, I'm going to need to go figure out like where that vertex point is. So we do the derivative, we set it equal to 0. And we get 2, don't we? So x is 2. And then what now? Endpoints. So we now have to evaluate f, the original function at 2, the original function at 0, the original function at 3. And that's, I mean, this is what we're evaluating right there. I'll do the 0. Yes.
F2 would be 0.
F
would be, yeah, would be 0.
F of 2 is 0. And how about f of 3? I think it's going to be 1.
Yeah, we got that.
Is it 1? Should be 1. It should be 1 because it matches with this one, right? Because we have to look like x2, but if we're letting x be 3, it's 3, 2, so it better be 1. So I've got more on my list, don't I? I've got f of, so this first one means 2, 2, right? 2, 2 is 0. F of 0, 2 is 4. And then f of, well, 3, 2 we already had. It's somewhat exhausting at this point. Last line, L4. So on your test next week, I'm going to give you a boundary. It's going to be a 16-sided polygon that you're going to have. No, I'm just kidding. Right? No. Well, we still haven't seen anything interesting yet that, other than that one line that was a diagonal, the hypotenuse of the triangle, we haven't really seen anything more involved. Yes?
So we're learning how to do it on the perimeter of the domain. Are we going to figure out how to find it on a closed interval like the middle of the domain?
We are doing that. We are, okay, so we are, the question was, right now we're moving along the edges, but what about the inside? Our first step that we do when we are finding where the partials are equal to 0 is identifying every point on the entire domain where we might have maxes and mins. So you got to look at it this way. Let's say you have a function that does something like this, right? In Cal 1, if we don't restrict the domain, we take the derivative, set it equal to 0, don't we? And that gives us everywhere where these might happen, right? But if we go and we cut it off into a closed interval, let's say I cut it here, and I cut it here, then we already have these 2 points, right? Any others we would have got, we would throw out because they're outside of our interval. That's the first step of what we did. Now the second step is equivalent to just doing the endpoints, but now we got to go around the whole boundary. So we've got the inside covered. The inside's the easy part. The outside's the hard part. All right, L4. Let's see how fast I can do this. L4 has to look like 0y, right? Y is between 0 and 2. So all my points plugged in there is just 2y. That's a line. That's a line, right? So I'm going to call this a function of y. So all I want to do is plug in my 2 endpoints into that. You understand I'm not doing the derivative because it's a line. So now, plug.
0, 0, already 0? Didn't we find that in the previous?
Yeah, well, no, did we? 0, 0? Oh, we did that earlier, yes. 0, 2, did we do that earlier? 0, 2?
We did 2, 0.
We did 0, 2 also, so we know that that's 4.
Wasn't it 2, 0?
No, it was 0, 2, I believe. No, because we were right here. On L3, we wound up at that point.
The same
Yeah.
first
So basically, we gain nothing in this L4 step, do we? We wind up just looking at these 2 points, which we've already looked at L1 and on L1 and L3. So this is it. What's the absolute maximum of this function on this closed bounded region? 9. And then the minimum value? 0.
Sir,
Yes.
I missed the first part. Where did you get F1 of 1? Why did you use 1 and 1?
We took the partial of this with respect to x, the partial with respect to y, and set them equal to 0.
Okay.
So that's equivalent to what we did last class. All right, well, got 30 minutes. Oh, now here we go. Oh, we didn't look at the picture. Should we look at the picture? Okay, so here's the surface that we were working with. And here was our domain on the ground. Here's the surface plugged in. Here's just, whoa, why did that happen? Come here. Come here. Okay, now here's the just the region plugged in. Take the surface out. So the green is our surface restricted to our domain, and then we found the points right there. There was our maximum up at 9, and then our 2 minimums of 0 occurred there. Look at that. Check this out. This is kind of interesting. One of our minimums, right here, one of our minimums, it occurred on L2. No, wait, where the hell is that one? It occurred on L3. It's right here though, right? It's right there. It's not at one of the corners. It's on a boundary, but it's not at the corners of the surface. It's actually within the line itself. Can you see it? It's right here. Interesting. Okay. I think I drew that a little off scale here. It's right there. All right. Let's look at this picture first. I'm going to do the picture of this one first. Look at the set. I want you to consider that set of numbers right there, or the set, our closed bounded region. Our region is D, which is a set of all points, ordered pairs. X is bigger than or equal to 0. What does that mean? X bigger than or equal to 0 means this. It's all this stuff down over here, right? Which is unbounded so far. But also, we must have, and that x squared plus y squared must be less than or equal to 3. Which means you've got a circle, right, with a radius of √3. And so it's wherever these two things overlap. You've got to be bigger than, be bigger than or equal to 0, but simultaneously you have to live inside this, or inside or on the boundary of that circle.
Also, y is
Oh, y is bigger than 0 also? I'm sorry, I didn't see that. I don't know how I overlooked that. Oops.
so it should be like that.
So it's basically the first quadrant of that circle. So this is not there. So it's just this in here. So we are taking just those points in that region, mapping them up into this surface, and trying to figure out where we get a max and min. This is the first time we've had one of our boundaries be nonlinear, right? Everything up to this point has been linear. Let's take a look at it. So here's I like this surface. There's something very pleasant to me about this surface. I don't know what it is, but there it is. Now we take that, there's our region, and we are going to put that surface in there. Let's just plug the points in the region in, take the surface back out. So it's this little green piece right here. We're trying to find the max and min of this. And Well, we're going to have to go along, different paths, like there, then around the circle, then down the side, right? 3 paths. And we should be able to find those points we have highest and lowest. Okay? Let's do it. If you don't know what that region looks like, you're going to have some trouble, right? You got to know what the region is. So let's draw a region. Okay. What's this point right here? That's root 3, 0. So I'll just label the axis root 3 there, and this is root 3 here, right? All right, let's do the first step first. First step is to find the critical points. And this part will take care of the inside. Right, Chad? Okay, so give me what are the partials here, Chad? With respect to x, it's y squared, okay. And with respect to y?
2xy.
Yeah, the 2, because the power rule on the y squared. So the 2 comes out, the x doesn't change, so 2xy. Christopher. Oh, there you go. Okay. What now, Christopher?
You set them equal to 0.
That's right. You set these equal to 0, and this should be pretty straightforward for us, right? Set that equal to 0. What's the only solution we get here, Christopher, from the first one?
0.
Y is 0, right? Y must be 0?
Yeah.
Okay, and then how about the second one?
Plug in 0 for y.
Okay.
Does that mean x could be anything?
That means x can be anything. We haven't seen this, have we? This is a first. See, for this one to be true, right? For your first partial with respect to x to be equal to 0, y has to be 0. So we have no choice but to let y be 0. But once y is 0, this equation's always true, regardless of x. Agreed? So this equation, partial of f with respect to y equals 0, right? The solution to this is basically all x between 0 and root 3, because we're only allowed to look between 0 and root 3, right? Does that make sense? So if your y is 0, right, you're down here, but all of these points along here, every single one of them is a critical point, every one of them. And that, initially you might think, oh crap, how are we going to test all those points? But it's not that big of a deal, because what's the function's value if y is 0? It's 0. So all along this edge, the function's value is 0. So even though my critical points look like this, they all look like x0 with x between these. It doesn't matter, because if I take my function and evaluate it at any of these points, I get 0 regardless. Lucky for us, that function behaves that way, all right? I know this kind of looks like what I was doing when I was moving along L1, L2, L3 earlier. It kind of is, because our critical points all live on this line. Do you all follow me? So now let's talk about the paths around. All right, let's go around this thing. Should I do L1? No, because we already know what happens, right? So really, we should just do this one and this one. Yes? So I'm going to call this one, let's see, Paul? Okay, this one right here. What do you want to call that one? L2? That's fine with me. How about C1?
Okay, so L2 wasn't fine with you.
No, I'm okay with that. I'm suggesting perhaps C. Now, would it matter? At the end of the day, does it matter? No. But I've been using L because of line. I mean, someone could be real anal about it and be like, L is for lines, man. But I'm with you. Who cares?
Because L1
L can,
we just did.
yeah, L1's here. Call that L. I don't care. Maybe L doesn't stand for line anymore. Who cares? L2, L3. All right? We're just moving along the curve. All right, so Paul, what do we got on L2? What do our L2s look like?
Do we want the critical points, or what do we want?
No, I want to know what all the points on L2 look like. You've got this one. You've got it.
And the gravity x squared comma y squared. Makes sense?
Let me help a little bit. If you're on L2, you're on the circle. If you're on the circle, you satisfy the equation of this circle, right? That may not have helped. So what is the equation of the circle, Paul?
X squared plus y squared
Is
less than or equal to 3?
so just the circle part, not the inside. You don't need the inequality anymore. So equals. So let's see, on L2, we've got to look like this, right? Solve that for y.
Oh, do we have to solve for both x and y?
Just y. Okay, just y. So if we solve for y, we take the x to the other side,
It's squared.
square root it. Now, technically we should be doing plus or minus here. We should have a positive and a negative answer. But because we're in the first quadrant, y can't be negative, so we're just going to take the positive square root. Y'all agree? Does that help? So, sticking with you, Paul. What do our points look like here?
Could we make it x
Mm-hmm.
square root of 3 minus
There you go. See, to live on that curve, your x-coordinate has to be, well, some x, and your y-coordinate has to be the square root of 3 minus x squared. Now, we do have a restriction. I'll let you go, Paul. That's it. Domingo, what is the restriction we have on x here? If we're going to use this for L2,
X has to be between 0 and the square root 3.
0 and root 3, right? So now what? I've forgotten. What do we do? Plug this is the kind of the template of what our points look like. We want to now map them into the surface. So plug them into the function of two variables. So we have f of x comma square root of 3 minus x squared must equal, well, isn't that nice? Right? Isn't that y squared nice? Right? Because you're going to just leave x alone, and then you're going to replace y with that, but then you're going to square it. So you're going to be taking the square root of 3 minus x squared and square it. So the square root goes away, you get this. And this is the first time we've had this. We have a cubic function. That's okay. I'm not afraid of finding the maximum or minimum of a cubic function on a closed interval because I have the derivative, right? I just take my derivative. This right here is a function of a single variable now. So I take my derivative. My derivative of this is 3 minus 3x squared. I set that equal to 0. And I think I'm going to get two solutions. Plus or minus 1. But I only keep the positive answer because I'm over here in the first quadrant, right? So only x is 1. All right. So what would be next?
Plug 1 into the 3 minus.
Yeah, so now we're gonna go in here and we're gonna figure out what, well, yeah, into this, right? We want to know what f of 1 is. What else do we want to know?
Square root of 2.
F of, hold on. I'm still looking like within the framework of this right here. 0, the two endpoints. I never put them, well, they're over here. F of 0 and f of root 3. So plug those in. I'm going to plug them in right here. So what's f of 1? 2. F of 0, 0, and f of root 3 is weird. It's 3 root 3 minus what? 3 root 3 again. Yeah, it's 0. I think it's easier to plug root 3 into this one right here. Because if you go root 3 right here, you square it, it becomes 3, and 3 minus 3 is 0, so that's gone. Now these correspond to some points on our surface, so let's write those down. This is the point f of something something. This one is f of something something. This one is f of something something. So what are those? I know it's 2, 0, 0, right? What's this first one right here? 1. And then you have to plug 1 into this, so root 2. And then the next one is 0, root 3. And then this one is root 3, 0. One more to go. L3. I'm not going to do L3. Here's why. If we move along L3, then what do all the points look like? X is 0, right? And if x is 0, what's the original function's value? 0, right? So, I mean, you can go through the work yourself, but you can easily see that if you're anywhere here, x is 0, and that makes that 0. So we've already concluded in the very first part of this problem that anything along here was 0, right? We've concluded anything along here just now is 0. The only thing we have interesting happening is along this circle. And what we discovered was that the values of interest to us are these two, which gave us 0, and then this right here, which gave us 2. So what is the maximum value of this function on this closed bounded set? 2. It happens here, which happens to be on this circle, somewhere around there. And then the other information is that the minimum value of the function is 0. And where does that happen? A lot of places, right? Along the axes. Yes?
I have a quick question. When you plug the f of root 3 back into the 3x cubed, or minus, yeah, on the second half of the negative x cubed, how'd you get root 3 of root 3, or 3 root 3?
I'll just write that as root 3 times root 3 times root 3. Right? And then these two together are 3, and then you have root 3 still. Yeah, someone blurted it out, so I was just like, okay, I'll go with that. I mean, I figured, yeah, okay. Yes? What do you think? Let's see if there are any more examples. I think that might be the last one. Oh, no, it's not. All right, this is a good problem. And I don't know if I'll finish this. Let's just look at it first. Find the volume of the largest rectangular box with edges parallel to the axes that can be inscribed into an ellipsoid given. So you have this fixed ellipsoid, right? So you got this egg, and inside of that egg, you want to inscribe a box. And there's all sorts of ways you can do this. You can make the box very tall, right? But it becomes narrow, doesn't it? It's touching that edge. It's really kind of hard to see. But that black dot represents the fact that it's touching just the edge of that ellipsoid. I can make it very short, right? So it's not as tall, but now it's wider. And that has a volume. Now notice I have the computer calculating the volume for me. And as I move that X, looks like I've got a pretty good volume there. 7, 7.5, 8, 8, 9. But something happens. Once I go past this like critical place, the volume starts shrinking. So we're trying to find out what the biggest volume we could possibly get into that ellipsoid is. Okay. How the hell are you going to do that? All right, so what is this section about? Maximizing or minimizing a function of two variables, right? If somebody right now gives us a function of two variables, we can be asked to find the local maximums and minimums, and we can be asked to find the global max and mins so long as we're on a closed bounded region. Agreed? All right. What is it that we are trying to maximize or minimize here? Yes, we don't want to make the length and width as big as possible. We want to make the volume as big as possible, right? So we want the maximum volume. Well, if I want the maximum volume, that means I need a volume function, don't I? I need a volume function. So if we have an ellipsoid, then every point on that ellipsoid must satisfy that equation. This one right here, right? If you live on the ellipsoid, if you give me an x, y, and z coordinate, I'll move it. If you give me an x, y, and z coordinate, the x, y, and z, when plugged into this, should give you a true statement up there, right? Okay? But if this point right here, why don't we make that point the corner of our box? All right? Make that point the corner of our box. Then our box would be drawn in here and look something like this. Do y'all kind of see that? It's important that you see this. So what is the volume of that box? In terms of this point, if somebody gives you this point, x, y, z, what is the volume of the box in there? 8 x, y, z. Where are you getting 8 from?
So, our x, y, z coordinate, I'm thinking of this as an eighth of our box.
That's right, it's an eighth of our box.
Because it's from the origin to that point, and since our ellipse is centered at the origin, we should be able to fit 7 more of those by reflecting it across the x and y axis. Sort of like we have 8 quadrants.
Exactly, because we have 8 quadrants. When we have this x, y, z coordinate and that goes to the edge, we're only in one of the octants, right? So the box goes down to the ground, but then past the ground on the other side. It goes backwards past the plane, this wall, and backwards. It's hard to see here. I mean, even when I bring up this picture, it's difficult It's difficult to see it, but, well, you know what? Maybe I can, stupid. Sometimes I forget that I actually put this in my code. Okay, so look, that's us at the XYZ. Okay, that's us coming out X, going over Y, going up Z. There's my point. So if you say that the volume of the whole box is just X times Y times Z, you're missing all the other octants back there. Make sense? Because it's only one piece. So we need to account for that. So what we do is we make 8 copies of that for each octant. Yeah? So here's what we've got. How are we doing on time? 34?
Sir, how'd you know the center of the ellipsoid was at the origin?
Actually, by this formula right here, because this is...
Nothing subtracted.
That's right. There's nothing subtracted in there.
Okay.
Yes.
All right.
Good question, though. So what here? Remember, we said we want to try and find the maximum and minimum, or maximum of something, right? The maximum volume. And right now, here's what we can say: the volume of that box is 8x times y times z. Right? But where does the ellipsoid come into play then?
The ellipsoid gives us an X, Y, and Z.
Well, it tells us what x, y, and z it has to satisfy, but look what I'm asking you to find the maximum of here. The volume, right? Maximum volume. And right now, this volume is a function of how many variables? 3. And everything we've done has been maximizing or minimizing a function of 2 variables, not 3. So you can't do this yet. Well, I mean, you can, but you can't do it as it is. You have to make this a function of 2 variables. So how?
The old one variable constant?
I'll let it go.
No one hold one constant, because then that fixes our box. It doesn't let our box adjust in all directions. Right now, this is an arbitrary, right now, this is just x, y, z, right? This could be anywhere. But you have to be touching the ellipsoid, don't you? Which means that you can take this equation and solve it for any of the 3 variables. Take that and plug it in there. It's not as bad as it looks. 4z squared equals 36 minus 9x squared minus 36y squared, right? That's what that is?
Okay, so it's
And then you have to divide by 4. And then finally, you have to take the square root. Z equals square root. Now, I'm only going to do the positive because I'm going to assume that my box that I'm drawing, the x, y, z, that the z is up, and then all the other copies go into the other octants. So there it is. Now, rewrite this. V must equal 8xy, but the z is not free to be whatever it wants to be. It has to live on that, so the z has to satisfy that. So that whole expression gets plugged in for z. 9 minus 9/4 x squared minus 9y squared. And now you have a function of 2 variables. I could call this v of xy. I'm just about out of time. So what would it take to find the max and min of that? Well, do you have a domain restriction?
Yes.
You do? What's your domain restriction? What is your domain restriction on x and y? This is somewhat tough to figure out, but
It's an ellipse with an x, or
where the hell's my
we
mouse?
are rated. It's an ellipse.
It's an ellipse, yeah. I agree, it is.
Either way.
Basically, think about this. If I were to come in here and just take a slice of this right through with the XY plane, right? When I slice that, that image on the XY plane is an ellipse. And that's basically the X's and Y's that are allowed to be plugged in have to come from within that ellipse.
Do you have to solve for like the foci and all that, like you did?
Well, what we know is if we cut it, right? If we cut it through with the XY plane,
Yeah.
Z is 0. So if Z is 0, this equation becomes 9x squared plus 36y squared equals 36, right? That's what happens when I slice it right through the middle. Then I divide everything by 9. Right? And divide by 4, I guess. That's an ellipse. This is an ellipse, isn't it? So let me draw it because I'm really almost out of time. So if I draw this, it looks like this. 2, -2, this is my x-axis, my y-axis goes up 1 and -1. So we have this shape ellipse. That's the domain. It's a closed bounded set. You give me any x from in there. Okay, so imagine you just go out, you pick out some x and y, and then go up z, hit the ellipsoid, and draw your box. So we are only allowed to look where, though, because remember the problem, the way we have it set up.
The first quadrant.
Yeah, we're only supposed to be looking in the first quadrant. So this piece right here is our domain. So I am out of time, but let's appreciate what torture would be in store for us at this point. You would have to take the partial of this with respect to x and then with respect to y. All sorts of product rule, chain rule, set those equal to 0. Get any critical points, save those. Then start moving around this boundary. This is a tedious problem. Can you tell it's tedious? We're not going to do it. But can you see how this would be bad? I mean, just the derivatives themselves would suck. Next section, we'll be able to do this in a snap. Well, not a snap, but a snap compared to this. All right? I thought I was going to talk about the test. Yeah, I mean, I can be quick. That way, at least over the weekend, you have an idea. All right? Test is next Wednesday. So you ready? Here we go. I'm going to tell you what you should expect. You should be able to find the domain and sketch the domain of a function of two variables. You should be able to show me that a limit of a function of two variables does not exist, which means, well, you find some sort of path that's different when you come in different ways. This will make more sense when you go back and review.
Is this going to be posted on Canvas? Like, no?
What I'm saying right now is all I'm saying. Yeah, we'll talk next class about what you can bring. All right, let's just get through this.
Are you still recording or no?
I'm still recording. But you never know. Technology, yeah, I think we're still going. You should be able to find different order partial derivatives. So like differentiating with respect then to x, then y, then x again. So higher order derivatives. Use chain rule. So those trees that we did, remember those? You should be able to find the gradient of a surface at a specific point. You should be able to find the maximum rate of change of a function at a given point. So that has to do with the gradient vector. So directional derivative and gradient vector, you should be able to do those. Find the equation of a tangent line to a surface. There were 2 formulas, so you should be familiar with both. And then the rest of them, the rest of the problems are, find the extreme values of a function, local max, local min, that's last class. And then you should be able to, like saddle points and all that, then you should be able to find the global max and min of a surface on a closed bounded region. That's it. That's a lot. I understand that's a lot, but obviously I can't give you a problem that's going to take you 40 minutes and then give you everything else, right? So if I give you a problem like the ones we did today, they'll be pretty straightforward, but you got to be ready to do them, because I think the biggest issue you're going to run into in this test is time. So if it's going to take you 10 minutes to figure out what the heck you're supposed to even be doing, it's going to be a very challenging test. You should be able to just look at it, know what to do. And in terms of formulas, we'll talk about that, but I am going to allow you to bring kind of like reference sheet or something so that you can have all your formulas in one place. All right, that good enough? Yes? Question? I said I think I'm going to wait till after spring.